My name is Deepak Panickal. I lead the graph compiler project at XMOS. XMOS is a small semiconductor company based in Bristol. We design our own microcontrollers and DSPs. It's based on our own ISA. So to get more background on xcore.ai. So xcore.ai is our latest microcontroller that we have. It's high performance, low latency microcontroller. It has 2 tiles on it, and when I say 2 tiles, it really means it's basically 2 processors on the same chip, and it only costs a few dollars for the chip, and it has 512 kilobytes of SRAM. So we want to make everything fit in the small size we have, right? And we are targeting AI on the edge, so that's where the graph compiler comes in. We are trying to use we have developed an MLIR-based graph compiler to optimize AI models to be deployed on this chip. Now, in this talk, I will outline our workflow, talking about what we have done to reduce memory throughout our workflow, and also talk about 3 MLIR passes that we have implemented as part of memory usage optimizations. All right, so first let me talk about the unoptimized workflow, right? The basic scenario. In this case, a machine learning researcher would use TensorFlow or PyTorch to design a model, and then that would go into a TensorFlow Lite converter, which is where it gets lowered to TensorFlow Lite, which is a subset of TensorFlow. And that TensorFlow Lite model can then be deployed on a TensorFlow Lite interpreter. So it's Lite for microcontrollers interpreter, that one, yeah? Now this will work on our chip, but it will be very slow because we are using reference kernels, and they are not optimized for our vector unit that we have on the chip. So this is a very slow way of doing things. Now, let me add in the graph compiler to this, right? So at this point, the difference here is that we have a graph compiler that we have developed, which we call Xformer. Now, the difference is that the tflite model is now consumed by the graph compiler, and it outputs an xcore model, which is just a model which has xcore optimized operations in it. And if you talk about in dialects, we go from TensorFlow Lite dialect to xcore dialect and back to TensorFlow Lite dialect, so that these optimized operations can be run on the interpreter that TensorFlow provides. Now, one thing to mention here is that we have a neural network library here, which contains these optimized operations. And we are still using the interpreter here, right? And obviously, due to that, there are some cons. So what are the problems, right? And we want to avoid using the interpreter. So for us, as an embedded device, code size is critical. We only want to include code for operators that are used in the model, because we really don't have space on it. And we want to remove any unnecessary runtime overhead, right? So we are using this open source project called tflite-micro-compiler. Now, this is a tiny open source project. This was actually developed by some automotive companies some time ago. So what it does is that it actually uses the TensorFlow Lite interpreter itself and logs runtime information, and it generates a C++ file for the model. And that's the GitHub link to the project. So now adding this onto the workflow, this is how it looks like now. So we have Xformer, the MLIR-based graph compiler, and we have integrated this tflite-micro-compiler project. And now the difference is just that the output from this is a C++ source file. So when we pass in a TensorFlow model, it comes as a C++ source file as the output, and then that can be compiled into a binary. And at this point, the binary would only contain operations that we use. So in this way, we have kind of removed all the superfluous code from the binary. Now, let me talk about an example here, right? So let's take MobileNet v2. So this is a model that you can just download off the internet. So I'm taking a case where it has an input of 160 by 160 by 3 as the input image, and an alpha of 1. And for those who are not familiar with it, alpha really defines the amount of compute in the model. So by increasing the alpha, you increase the number of weights, thereby the size of the model. So if you use an alpha of 0.25 here, this model will already fit on our chip because it will fit within the 512 kilobytes. But using an alpha of 1, you can see the RAM used in the unoptimized case is around 1.3 megabytes of RAM and around 2.6 megabytes of binary size. So this will not fit on our chip. So after doing the initial optimizations, so after using the graph compiler, there is a slight difference. So it goes down to 1.3 megabytes for RAM and 2.3 megabytes for the binary size. So this will still not fit on our chip, but the difference here is that now it will at least run fast, right? And you can see by the end of the presentation, with these three passes that I'm going to talk about in MLIR, the model will fit on the chip. So let me move on to the MLIR passes. So the first one is memory plan analysis pass. So what does that do, right? So it plans the tensor arena and allocates offset for tensors in the model. So if you look at this snippet on the right, you have a convolution which takes in an input of 160 by 160 by 3 and outputs 80 by 80 by 32. That's the output from the convolution. So both these tensors have to be allocated somewhere in the tensor arena to execute the convolution. And so that's what the analysis pass does. And before I move on to the actual pass, I just want to talk about the dialect used here, right? So this snippet on the right is the same as the what I'm showing here in IR form. So this is actually in TensorFlow Lite dialect, and this is how it would look like in MLIR IR form. So where you have a tfl.conv2d and a tfl.depthwise conv2d. So from here on, I'm only going to show the graph. I'm not going to show the MLIR IR form. So let's move into the algorithm. So the first step that we do is we walk the graph. We walk the entire graph, try to find all the non-constants in the graph. So if we take look at this snippet here, filter and bias are constants, whereas inputs and outputs are non-constants. So filter and bias don't have to be allocated, whereas non-constants have to be allocated. So we kind of find all the non-constants. The next step is we prepare a map of first used and last used ops. Now this is done to aid in the allocation algorithm that comes later on. So we use the liveness analysis pass in MLIR and try to identify the simultaneously alive tensors. And if you think about it, the largest simultaneously alive tensors, so the largest group of all the alive tensors, will define the peak memory usage of the graph. So reducing this would mean your model is using less memory. The next step is we identify ops that can be overlapped. So in this case, we know this is the pad operation, and we know that we can overlap the input and output for this pad operator. So they don't need to be allocated separately. We can reuse the input and output buffers. Now, we are capable of doing this only because we are doing this optimization at the IR level, right? At this level. And similar to the pad operation, we have other operations that we can use. Do the same thing with, where you can do partial overlap or fully overlap them. Now, the next step is we actually do the allocation. So the allocation algorithm is similar to the one that is there in the interpreter, but now we are doing it in MLIR, right? So we're doing it at a much higher level, and we want to minimize the total memory used while avoiding fragmentation. And this is done by sorting these tensors in decreasing order and then picking the largest one, and so it's a greedy algorithm that does the allocation. And finally, we prepare the allocation plan. So the allocation plan is simply an array of offsets, one for every tensor in the model. So for the constants, we output like a -1, and for all the non-constant tensors, it ends up becoming a positive integer, like that one here. So at this point, the memory plan analysis is done. We have overlapped buffers and hopefully found an optimal allocation strategy, right? So going back to my example, for MobileNet V2, we were at 1.3 megabytes for RAM and 2.3 for the binary size. After doing arena planning, which is the memory plan analysis, we have gone down to around 798 kilobytes for RAM, and there's no difference in binary size because we haven't really done anything for that. Now, let me talk about the next optimization, right, which is the operation split pass. So what do we do here is we try to split operations into multiple ops to reduce peak memory usage. So again, if I point to this snippet here for convolution and depthwise here, to run this convolution, you need to allocate the input, which is 160 by 160 by 3, and the output, which is 80 by 80 by 32. So both of these have to be in memory. But on the other hand, if we try to split this convolution into 10 pieces, right, and we don't execute them in parallel, we go through them sequentially, that means we can save memory. I mean, it's a trade-off, right, because we are increasing compute, but because we can't fit the model on the chip, we have to do something, right? So it's a trade-off. So now let me move on to the algorithm. The first thing we do is we annotate ops to be split in the model. So in this example here, we have annotated 3 operations in the model. So the annotation can be done using command line options, or we can do it using auto annotation, which is still partially working, and that's done using liveness analysis again. So we annotate groups of operations in the graph, which we think are using the peak memory, right? And we want to split those. The next thing we do, so we start at the bottommost operation in the annotated ops. Then after that, we insert stridor slices and concatenation. So here, what we've done is that, so one thing to point out here is that we also decide the number of splits. So this is something that we can specify by the command line options. So here we've decided the number of splits as 6. So we are now inserted slices and a concat just below the depthwise convolution. And next we raise or hoist these slices above the depthwise convolution, and that's when we actually do the splitting. So we have raised the 6 slices above the depthwise convolution, and we have split the model into 6 portions. Split the operation into 6 portions here. And one thing to notice here is that there will be a bit of overlap in the input versus the output because of the way convolution works. And that means that we will actually do a bit more compute than what we used to do before when we just had a single op. But again, that's a trade-off. And the next step with the operation split pass is we redo this raising of slices over and over until we reach the top annotated op. So the next op here is the pad op. So we go once more higher. So now we have split the pad op here into 6 portions. And now we go one more because we had originally annotated 3 ops, right? So we go once more, and we have now split the 3 ops that we had originally annotated: the convolution, the pad, and the depthwise. So now let's see what impact this has had on the example, right? So going back to the example, after doing operation splitting, the RAM used has now gone down to 363 kilobytes, which is really good. The binary size has slightly gone up, but that will be solved in the next pass. So the binary size has gone up because now we have actually increased the number of ops in the model, right, by splitting operations, and that's why the binary size has gone up. But the offloading to flash pass should take care of that. So what does this pass do, right? We offload weights in the model to a flash image. The idea is quite simple. We have constants in the model, and we want to move them out of the model and put them in a flash image, which we can then stream in at runtime. So moving on to the algorithm, here we have, you can see that filter and bias are constants. So that would be an example of something that we want to move to flash. So we conditionally insert xe load constant ops. So now that is an op that we have in the xcore dialect. And the condition here is that we decide which ones we want to lower or which ones we want to load from flash. So here we have decided that the pad has a paddings parameter which is constant, but it's only 8 integers, so it's too small. So we don't want to lower that to flash. Whereas that depthwise has a filter and bias which are large enough to load from flash. So we have inserted this load constant op here to denote that we want to move those later to flash. So the next step that we do is we want to change the execution order. So for this convolution here, we want to load the data for the convolution just before they're needed by the convolution, right, when we execute them. We don't want the tensors to be alive in memory longer than they need to be, right? And so for that, we use the move before function that's there in MLIR to specify that we want to just move these operations just before the convolution here, and that thereby changes the execution order. And then another thing that we do is we combine ops that are to the loads that are going to the same op. So we combine loads that are being used by the same op. So here there are 2 load constants going to the same convolution. We combine them together and lower them to a single load flash op. So at this point, we have changed the graph to have load flash ops in there, and this op will then later on stream in data from flash. And it's also at this point that we move the data into a flash image in the compiler, and then later on this can be flashed onto the device, and thereafter it works. So now going back to the example, we were at 363 kilobytes for RAM and 2.3 megabytes for the binary size. But after doing this offloading to flash, we are now at 384 kilobytes for RAM and 488 kilobytes for the binary size. So the model fits now, and that means we can actually run it on our chip. So that's great. And actually, that's what I wanted to talk about in terms of the MLIR passes. And now I'll just talk about challenges and future plans. So in terms of challenges, I want to bring back this slide again. So we, like I said, we have developed an MLIR-based graph compiler, right? But we depend on a lot of different projects. We depend on TensorFlow. We depend on the MLIR project. We depend on LLVM because of that. And there is TensorFlow Lite micro project. There is TensorFlow Lite-micro-compiler project. So there are a lot of code bases here, right? And TensorFlow uses Bazel for building. LLVM and MLIR prefer CMake for building. So one major challenge here is identifying prior art, right? So we don't want to rewrite code. We want to reuse as much code as possible. And you do end up seeing similar things being done at different levels in TensorFlow and in MLIR. So that's one big challenge. Another big challenge is finding out what is the correct way of doing something. So one example is, in MLIR, you can use match pattern function to get the data from a constant. But that's not the only way for doing that. I mean, there are different ways of getting data from a constant, right? So, and some ways are better than others. So that's another challenge that, it's quite likely that when I go through the code base, I stumble upon some new way of doing something. So that's another challenge. And in terms of future plans, we want to improve our analysis pass. We want to have a better execution order. And the idea is so that we can actually run even larger models on our chip. And finally, I want to talk about our experience with MLIR. Yeah. So the MLIR framework has made it really easy for us to add optimizations and productize our AI tools. So the tools, it's something that's actually available on PyPy to install and use for anyone. We are using a lot of code from TensorFlow and MLIR. And being able to work at the right level of abstraction, especially when I spoke about the memory planning path, looking at different ops in different dialects and seeing what to do with each of them is really intuitive. It's really easy to think like that. So it has made it really easy to productize our tools and deploy such models on our small chip. Right? So that's it. Thank you. And one thing to point is that all the code that I mentioned, for the compiler and the runtime is available publicly on GitHub. And yeah, thank you.
Yeah, thank you. So if there are questions, there are 2 microphones here in the room. Also one that can go around. Sure.
Hello, thank you for the nice presentation. I was just wondering which dialect you guys use to perform the splitting right now. And
so we are doing everything in either TensorFlow Lite dialect and xcore dialect, which is our own dialect, and that's it. We are not lowering to any other. So it's all done at the high level itself.
Okay,
yeah.
So you're not using linalg or anything?
No,
like
no,
that.
no, no.
Are there any plans to use this in the future, maybe?
So I've been looking at we've been looking at ERI project, to see if we can reuse So I know there've been some work happening with the microkernel dialect where you can kind of hook in, you can match a DAG and then you can hook in operations. So I'm hoping that maybe we can do something like that when we move towards Cogent. But one thing to note here is that we have an LLVM compiler, but that does not support the vector unit. So for the vector operations that we have on our chip, we are actually still handwriting assembly for it. So Cogent is not still an approach that's easy for us. So we still have to use some kind of handwritten assembly. Yeah.
So and right now, so for each op that you split, you perform a pass that is specific to each operation, or is there a more generalized way that you found to do these splits?
It is quite generic, actually, but we do have to target, you can't use the same splitting method for a pad op and a convolution, right? For the convolutions, for all of them, you could probably do the same. We can actually redo the same functionality, but not for pad operators. So yeah, you have to specify them separately, yes. Yeah.
Okay, thank you.
Okay, are there any other questions? Yeah, can you go to the mic?
Thanks for the talk. I have something just, When you were describing the arena planning problem, that sounded to me just like a classical register allocation problem.
Yeah.
And technically, the bufferization dialected infrastructure was designed to do that
Yeah.
at tensor level. And we all know that in practice, it doesn't do that quite well and in all cases.
Yeah.
But even if you are working on your own dialect, you could have extended the interfaces and tried to work around that. Have you considered that, or have you given that up because the design doesn't match you? I just want to know.
So I have like, I mean, I've not tried it myself yet. I know like the bufferization dialect does offer methods to do memory planning, right? Planning like that, but I'm not sure if it would be applicable to what we are trying to do. But it's something that I definitely want to check out. You know, I want to try to see if there is stuff in there that we can actually reuse. Yeah, yeah.
Thank you.
Okay. Any other questions? We have time for one more question. Okay, if not, then thank you very much.
Thank you.
And the next talk is at 2:30.